So the main focus of today's video is to remind you of the other tests, of the tests that we've done leading up to today, and to really focus on the alternating series test. So we've already done these direct comparison tests, limit comparison tests. These tests will not be on the AP test, so for that reason, and we've already gone over these. I've already filled in these notes and remind you of those things. So direct comparison tests, that if we know that something converges and what we are comparing it to also is less than that, then that series will also converge. So we don't know about this, but we're going to compare it to something that we do know something about. So we don't know what A sub n is, and it doesn't matter which. It kind of doesn't matter which one you call A sub n, especially with the limit comparison test. If we know that something diverges and the series that we don't know about is greater than it, then it'll also diverge. Let's look at a couple of those examples that we've already done. So we have 1 over, and we're really focusing on these these are infinite series. And just like in Algebra 2, in pre-calculus, the numbers don't really matter at infinity. What really matters is that x, and we're going to pick the largest thing in there. And so we have this, really, the largest thing on the bottom is 3 to the power of n. That 2 kind of doesn't matter. So we know that 1 over 3 to the n converges by a geometric series. There are also some other tests we could use, but let's just focus on that. And I just want to remind you at this point that the sum of a geometric series is going to be the value of the first term. And since we're starting at 1, for this one right here, we're going to start in the same place. The first term is 1/3, and we do 1 minus the ratio. The ratio in this case is 1/3, because our series starting at 1 is going to be 1/3, 1/9, 1/27, etc. And so that gives us 1/2. So we know that 1 over 3 to the n converges. And we know that when I make the denominator larger on the bottom, then it's going to make the whole function smaller. So what we don't know is going to, we're not sure about that series just by looking at it. But I do know that that's going to be less than 1/3, and I miss this power to the n. So I'll just put that back in there, right there. Since it's going to be less than that, then it's going to behave the exact same way. I don't know what that sum is. I will only ask you to find, remember, I'll only ask you to find sums of geometric series. That's the most important one. We also have, not harmonic, but telescoping. Don't know why. Those are the two main ones that we're going to ask you to find the series of, the actual sum of, excuse me. I don't know what that sum is, but I do know that since each term is less than 1 over 3 to the n, then the sum is going to be less than 1/2. So we keep adding smaller things to it. So I've already done all these. These are all can be done by the simple direct comparison test. So this looks like 1 over n squared. That plus 1, again, really doesn't matter. We don't know what the sum of 1 over n squared is, the infinite series. But I do know that it's a convergent p-series, since that power is greater than 1. It's 2. And I would just write that 1 over n squared is less than 1 over n squared plus 1 is less than 1 over n squared. You don't have to do any really math on that. That's just kind of, we all know that. You could double check that by doing some math. And these are all positive series, by the way. If you write out positive sequences and series, then that will also converge by the geometric series. So this, again, since we're talking about an infinity, the only thing that matters is the greatest thing on the numerator and the denominator. So we have n over 5n squared, which is like, we can reduce that, 1 over 5n, and those n's cancel out since the n is never 0. So we can do that. So we know that 1 over 5n diverges. You could say that diverges by p series, or it's a multiple of the harmonic series. And I know that since I'm subtracting in the denominator. That makes the whole thing larger, like 1/2 is greater than 1/3. So if I subtracted 1/3 and 1/2, so that is greater than that. So that series will also diverge. I don't know the sum of any of those. So you either need to use a direct comparison test, you need to know or state that what we're comparing it to and what we know is either less than that or greater than that, appropriately. With the limit comparison test, you don't need to kind of figure out, well, is it greater than or less than what we're comparing it to? Those are both comparison tests. But we do need this limit as n goes towards infinity when we're comparing it. And if we get out some number that is both positive and finite, so our number is in between 0 and infinity. So again, we're going to look at, well, what does this look like? So we have something that's messy. So we have 5n squared, 7n cubed, which is like 5 over 7n, or we know that that's, again, a multiple of a harmonic. So, and then since it looks like that, it's going to also diverge. So once you recognize the limit comparison test, you can just say, we know that this looks like this 5 over 7n, or pulling out the factor. You can compare it to 1 over n. I compared it to the original series that wasn't even simplified. You could simplify all that stuff. So you do need to have that work when you use the limit comparison test. Again, the limit comparison test is not on the AP test this year, but it is still good to know. So we have what we don't know, but we do know because we know this basically behaves like something that we're comparing it to. It could have been 1 over n if you wanted it to. But this, since I actually kept those factors, I did get out a 1, and 1 is my L, and 1 is positive and finite. 1 is in between 0 and infinity. That's kind of it. And so again, I did these kind of quickly. We just know that this thing looks like 1 over 5n over 3n squared, which converges, P series. So therefore, what we're comparing it to will also converge. And I would rather do the limit comparison test because I don't know whether or not that thing is less than or greater than that. Limit comparison test is the best on that one. So we just pulled out the thing that was greatest n squared on the top and on the bottom. And we know that one converges because it's like 1 over n cubed, P series. This is going to converge by the limit comparison test, not by the P series. We're comparing it to a P series, but it doesn't converge because of the P series. We'd have to do that limit on that one, write out the limit and write out the work and say that you get out a number. The square root of n squared is like, so I went ahead and simplified that to 1 over n. We know that 1 over n is our harmonic, the most important one that we have, and that one will diverge. So since that I put a converge right there. It diverges by the limit comparison test, excuse me. So we know that 1 over n squared similarly converges. So therefore, what we're comparing it to is going to converge. Now this one, and all of these are just simplest to do limit comparison test. We could have done the direct comparison test because we had this plus 1 on the bottom. So therefore, it's a little bit, the denominator is a little bit larger, which makes the whole function a little bit smaller. The ratio test is the most important one. I don't remember whether or not we went over that. It might have been a couple of weeks. So I'm going to go over that a little bit. I'm going to work through that kind of with you instead of ahead of time. So the ratio test really just says we're going to take the absolute value, and everything that we've done so far has been a positive series, and I think that's where they're going to focus on on the AP test. But absolute value, if ever, it could be all negative or alternating. If we can always compare the next term, and what do we have next and what do we have now? And what happens? What do we get out? This r doesn't, if the r is less than 1 or in between 0 and 1, we're doing absolute value, so this thing is always going to be positive. or the limit as it goes towards zero could approach zero, so it could be equal to zero. Or is it greater than one, or is it equal to one? Rarely will you have the equal to one. That really just means that you use the wrong test on that. So I'm going to say trust your instincts on that one. And the ratio test is really powerful. I always use it whenever you have this factorial. N factorial is in there. We got to use the ratio test. It also could work. It also works if n is your exponent. So those are the two main times that we have exponential series. Those are the two main times that we use the ratio test. So determine whether or not the series converges or diverges. So I'm not 100% sure, but I mean, I do know because n factorial is really large. But let's see what happens. What do we get out? So I'm just going to remind you that it's going to converge if our limit, our infinite limit, is less than 1, and it's going to diverge if it's greater than 1. So those are the two main things that we have. So we're going to do the limit as n goes towards infinity. I'm going to do it the exact same way that they do it with that in there. I'm going to write it out. I'm going to choose two different colors. So a sub n plus 1 is 2 to the n times 2 over n factorial times n plus 1. And then I'm going to, actually I'm not going to, I said I was in my head I was going to divide it, but we all know that division is the same thing as multiplying by the reciprocal. And so what happens? What is that limit as you go towards infinity? So what we have is we're going to simplify the things. N is the thing that's moving. So we have a 2 to the n and we have a 2 to the n on the top and on the bottom. So those things are going to cancel out. It's really important. We have an n factorial on the top. We have an n factorial on the bottom. And now we're going to look at that limit as n goes towards infinity. And what we have left is 2, everything else canceled out, over n plus 1. And what do we know about that limit? That is 0. And 0 is less than 1. So therefore, our series to the n over n factorial, n starts at 1 and goes towards infinity, will converge by the ratio test. Right? If this says show it by the ratio test, then you would do that, or you would just do the work and that would be fine too. So now let's look at this next one, and we're going to do, well, let's see. I don't really know. We have an exponential, we have a polynomial, so I can't use the limit comparison test. I can't use the ratio test. This factorial is really, you're stuck with using the ratio test whenever you have the factorial. So we have a bunch of different things. If we look at that other one, like before, these were all basically polynomials or polynomial functions on the top and on the bottom. But these, whoops, what did I do here? Oh, I hit add a page I didn't mean to. But since we have a polynomial and an exponential, whenever we have a mixture of those, we would have to use the ratio test. So we have the limit as n goes towards infinity of n plus 1 squared, and I'll put those absolute values in there. And then this n, when that n is on the exponent, then I usually just do n plus 2, which is the same as 2 to the n plus 1 times 2 to the first, and you add those things together. And then n plus 1 means I have another 3, kind of obviously. And then I'm going to multiply that by, I'll put that all in parentheses maybe, just to remind me, 3 to the n over n squared and 2 to the n. Now, I want to remind you right here that you can only cancel out things that are exactly the same. So n squared is not exactly the same thing as n plus 1 squared, But I'm just going to highlight the things that are exactly the same that will cancel out. So 3 to the n, 3 to the n. Whoops, and I copied this down incorrectly. My bad. N squared to n plus 1. And so that was a good reminder that, they have to be exactly the same. Could be some copy errors in there. Hopefully we're going to stay away from that. And if we double check our work, we'll see what we need to see. So we have the limit as n goes towards infinity of n plus 1 squared times 2 over 3 times n squared. So you could multiply this thing out, and actually it's not that bad to do that. On the bottom, I have 3n squared. And you kind of know at this point, we have 2 times n squared plus 2n plus 1. The most important thing is you have that n squared. And again, whenever you're adding things and you're going towards infinity, oops, I left out that n goes towards infinity, then what really matters is only the largest power. N squared is a thing that matters. So we have, we have a 2n squared on the top and a 3n squared on the bottom. So that limit is going to be 2/3. So 2/3 is less than 1. So therefore, what we're trying to decide whether or not it converges or diverges, that one will converge, since we had a ratio that was less than 1. Root test, not going to be on it, so I'm going to go through that real quickly. I use that root test whenever we have exponents, and we'll go over this more later, or you can look at the stuff on AP Central. Whenever we have an exponent, that's if the variable is in the exponent, or an exponential function. So I'm going to use the root test, and basically all of the n's go away. That's really what we have. Actually, the n on the exponent goes away. If the n is not being raised to that power, then that becomes 1. I'll just show you that real quickly. So those are the rules that we have on that, and I wouldn't focus on this too much right now. You can come in and ask questions about that later. So we have n to the power of n. Whoops. And actually, we want to do that nth root, the nth root of that. What is that? And again, if we get out a r, but this is an m, like whatever. They use r for ratio. You can use L. That letter really doesn't matter. So when I do that, this nth root cancels out this n right here, and what I have left is e squared. We're still going to look at that limit as n goes towards infinity. So we have e squared. And now this n, I'm just going to change colors on this one. The nth root, on the nth root cancels out this n. It doesn't cancel out the n. So it's kind of like saying if I have, and I will talk about this in a little bit. So we have e squared, which is a number, I don't know, 7 and some change over n, but n is going towards infinity. That is 0. So therefore, that thing will converge. And let's talk about this a little bit. So if I have 3 cubed, and if I take the cube root of that, that's going to give you 3. So that's saying the cube root of 27 is 3. And if I have the fourth root of 4 to the 4th, obviously I don't know what the fourth root of 4, or you can see that as, well, it's 4 to the 4th raised to the 1/4 power. And so that kind of cancels in. It doesn't, so it becomes 4 to the power of 1, right? So that's using our rules for the nth root is obviously the same thing as whatever this thing is to the power of 1 over n. So you could think about it like that. And then that cancels, that goes in and does that. It's kind of the same thing with e to the 2n. So it's really e to the 2n to the power of 1 over n. So if you want to do it like that, you could. using the nth root, or you just remember that those things cancel out. So that's kind of it. So we have now the limit as n goes towards infinity. And, and so sometimes you see the nth root and you have it power to the n. Or if you want to do that rational thing, you could. And technically we're inside of absolute values. We're taking the nth root of the natural log of n over 2 to the n. The whole thing is raised to the power of n. So those things cancel out. And what we have left is we have the limit as n goes towards infinity of the natural log of n over 2n. But what is that limit? And this is a good time to remind you about L'Hopital's rule. So if I throw in an infinity, I have infinity that's just scratch work, infinity over infinity. And so we would have to say that since the limit as n goes towards infinity of the natural log of n is infinity, and the limit as n goes towards infinity of 2n is infinity, by L'Hopital's rule, the limit of as n goes towards infinity of the natural log of n over 2n is equal to the limit as n goes towards infinity of the derivative of the top, 1 over n over 2, which is the same thing as the limit as n goes towards infinity. I'm just doing all this work, which is 0. For some reason that highlighter came back up. So therefore, this thing will also converge, what we were doing from the beginning. So since the m is, and 0 is less than 1, we were trying to figure out what that limit was. And did we get out a number that was less than 1 or greater than 1? And we got a 0, which is less than 1. So we would then write the limit, natural log of n over 2n. That series, that infinite series, I think n starting at 1, will converge by the ratio test. Sorry, by the root test. If you ever could use the root test, you could have also used the ratio test. Okay? That's the short answer on that one. Again, more time than was really necessary on that one. So if you didn't quite follow that, we'll get that later. An alternating series is a series that alternates. So we can use the alternating series test. So before, again, we had all of these positive series. Each thing, we call this a sub n, was positive. Now, each term can, if it's an alternating series, then each term alternates. And that's what an alternating series is. We can use the alternating series test if we know a lot of things. So if we, first of all, the first condition is it has to be alternating, right? A lot of times it's going to be in this form, -1 to the power of n plus 1. That'll make it alternate. And this second condition must be met. I'll actually change that to a 2. What this means is that it's decreasing. Okay? And it's always positive if I'm only focusing on this a sub n part. And I should probably, we'll change that to red. And we're just talking about the a sub n, not the alternating part. We're kind of done with that. So is it decreasing? And is that last term, is the limit equal to 0? So let's look at a couple of these things. And there's a great video on that, and actually I'll show it to you. If either condition is not met, the test is inconclusive. Specifically, if the second condition is not met, we could have used that test for divergence. At the end, we don't have 0. So if ever you're adding a 1/2 and a 1/2 and a 1/2 and a 1/2, then that test is going to converge. Even if they're alternating, it really doesn't matter. Because you don't know whether it's going to be, positive or negative. right? Those things don't really cancel out. The series may converge or diverge. You don't know. Most of the time, if that last one does not, if the last term is not zero, then it's going to diverge by the test for divergence. All right. So we have this harmonic series. We know that the harmonic series by itself, we know that thing diverges. But let's look at the alternating series test. Yes, before we do that, let me remind you of this thing right here. So we had the harmonic series 1 over n. That one diverges. It diverges for a lot of reasons. So we have 1 plus 1/2 plus 1/3 plus 1/4. And right before it ended, I knew that that one, those two terms are greater than 1/2. And then if I group another group of like 4 things, that is going to be greater than 1/2. So really I have 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And it's going to be really big. It's going to diverge. Looking at it on a number line, I have 1 plus 1/2. And really what we're saying, plus 1/3. And so this is what the sum of the first 3 terms are. And then I add a 4th. And even though these steps are getting smaller, they're still going to eventually bounce out to infinity, right? But if the steps are too big in this case, but if I had like a 1 over n squared, then those steps are so small, they're going to eventually stop. I know that's kind of crazy, but it's actually easier to see it with the alternating series test. With the alternating series test, you can actually see, and we'll actually look at this test. I'm going to change colors on this. And there was actually a better video by another professor that does this, and that I will post, or you can find it. Minus 1/4 plus 1/5. And it keeps going, right? So we have 1. So we're starting off at 0, and I'm going to go to 1. And I actually put this 1 right here. There's 1, and here, by the way, is 2. And now I'm going to, oh, but I don't even need that 2, excuse me. Now I'm going to subtract 1/2, so I'll actually keep my color red. And here's 1/2. We're going to subtract 1/2. Boom. So that's what we have right there. And then we're going to add 1/3. But 1/3, even if I add 1/3, I don't go past 1. I actually will get out to 5/6. So let's just call this number 5/6. Boom. We'll call that 5/6. And then, so here's 5/6 after adding the first 3 terms. Now if I subtract 1/4, I don't make it back to 1/2. I don't even know what that number is. And actually, I'm actually going to start doing it this way. And then now I'm going to add 1/5, but I don't make it back to this place right here. I'm adding 1/5 to it right there. And then I'm going to subtract 1/6. Then I'm going to add 1/7. So I'm actually going to converge to some number. I don't know what that number is. It's some number. At this point, I'm in between 5/6 and 1/2. I don't know what that sum is, but we are going to converge. And if you add enough numbers in there, you could say, and this is what we're going to do later, talking about the error, but how close do you want to get? And I'll get you there, right? How close do you want your infinite sum to be? And I'll tell you, or you can find out the number of terms that you would need to find what that sum is. So that is a very bad graphic of that. But there is a video where a teacher did a better job on that. So if those two things are met, so let's look at that. And I kind of showed you geometrically, visually, why this alternating series will converge, because it's kind of bounded. I don't know what it is. It's kind of like that 1 over 3n plus 1. I don't know what that sum is, but I knew it was in between, it was less than 1/2, in between 0 and 1/2. If you do enough terms, you can find out what it is. And there are multiple tests on that one. So let's go ahead and look at it. Well, the first thing is, does it converge? Well, is it alternating? Yes, it is alternating because you have a positive, then negative, positive, negative, and that dot, dot, dot says that, all right, we can say that it is alternating. The next thing, is it decreasing? So we would say that this is, all we have to do is now look at the sum, 1 over n. We're looking at a sub n, and actually we're going to write this out. Negative 1 to the power of n, 1 over n. And this is going to start at 1, so I need to change that to n plus 1, technically. So this is our a sub n value. And this is just the alternating part. It's kind of separate with the, after we know it's alternating, we only need to look at those other things. So our a sub n function is 1 over n. And we can just say that 1 over n plus 1 is less than 1 over n. That's true. Boom. And then the last thing is we would have to state that the limit, make that a little bit smaller, as n goes towards infinity of 1 over n, our a sub n, that's 0. Boom, we have the 3 conditions met. So therefore, this thing will converge by the alternating series test. And even if we had the alternating series, it's not really on here, I don't think, 1 over n squared, this one will converge by the alternating series test because it is alternating. 1 over n plus 1 squared is less than 1 over n squared, and the limit of 1 over n squared is 0. So let's look at this. Is it alternating? Well, yes, it is. So here I'm going to actually change this up a little bit. This means that it's alternating. Check that off. Now we're going to look at this part right here. So we need to know, that's the first part of it that needs to be true. So we have negative 1 to the negative 1 squared, negative 1 cubed, negative 1 to the power of 4, to the power of 5, etc. That makes it alternate. And now we need to say, well, is 1 over the natural log of n plus 2, is that less than 1 over the natural log of n plus 1? And that answer is yes, it is. And you could actually, there are lots of things that you could do with this one. But as long as you state that, are our denominators getting larger? Yes, they are, right? And even if it wasn't true at the very, very beginning, it's going to eventually be true. But it is true in this case. Like, you can compare the first couple of them. As long as you state that, you know the things that need to be true in order for it to use the alternating series test. And the last thing is the limit as n goes towards infinity of 1 over the natural log of n plus 1. Is that equal to 0? That answer is yes, because we have 1 divided by the natural log of infinity plus 1 is 0, right? And it's not a L'Hopital, it's just, whenever you have any number over infinity, it's going to get you 1, okay? So this last one, is it alternating? Sure, it is alternating. There's the alternating series part. Is it decreasing? I don't really know, but this is what, let's look at this, and hopefully something is kind of like screaming at you on this one. Is the limit, and actually that's most of the time really what we really need to focus on, is the limit of n over 10n plus 1 as you go towards infinity, is that 0? No, it is not. So we would say not equal to 0. So therefore, we cannot use the alternating series test. So alternating series test is not true to show that it converges. Alternating series test does not show that something converges or diverges. So we would say this one, number 2, does converge by the alternating series test. Number 1 does converge by the alternating series test. So therefore, there was another one. Well, what this says, so if you go back to our test for divergence, is the last term equal to 0? No, it is not. So therefore, whenever that last term doesn't equal 0, at the end we have 1/10 or negative 1/10. So we keep adding and subtracting those. We know that that does not, we can't make it doesn't converge. Even if it's alternating, it doesn't converge. So whenever the last term is not 0, it's going to diverge by the test for divergence. That comes in a couple of different ways. Divergence. I think I spelled that correctly. So that was my great example on that one. What about this one right here? Is it alternating? Yes, it is. This is the one I think and let's go ahead and do the limit. The limit is n goes towards infinity of the natural log of n over n. Does that equal 0? Yes, it does. The other thing that's really important is the n plus 1. The natural log of n plus 1, put that in parentheses, over n plus 1. Is that less than the natural log of n over n? And if you pulled out your calculator, you would see that it's really not at the beginning, but it is at the end. So it is eventually decreasing. What I really care about is at infinity, really. Does this thing decrease? And it does. And so in the notes that I posted online, I use a derivative to show that it was decreasing. That's really what that is showing. I'm going to show you one other way, kind of conceptually, and also to remind you of a couple of things. So we wanted to know whether or not, and this is kind of crazy-ish. So when we have, I have to remind, I didn't write down this, natural log of n plus 1 over n plus 1. So we want to show that the natural log of n plus 1 over n plus 1 is less than the natural log of n over n. And since we're talking about positive things, we're starting at, it's always going to be positive. N is greater than, starts at 1. So we have n times the natural log. We can cross multiply on that one. That's what I'm doing right here. Is that less than the natural log of n times n plus 1? And you can actually graph that one. As long as you state that, we're going to be all right. And that is true. If you have a calculator, you would see that. Or algebraically, this is kind of the next level things. It's, again, as long as we're stating that, we're going to be all right. And I know, and you know, that n is bigger than the natural log of n, right? That should be an n plus 1. So, since I'm multiplying by a bigger number, that's the thing that's going to grow faster. And if we actually had e, we have a natural log. So to kind of deal with those, we have e to the power n times the natural log of n plus 1. Is that less than e to the power of n plus 1? And I'm doing it this way for a reason, natural log of n. Well, we know that if I just kind of ignore that e part, whenever I have a natural log, that's the same thing as raising it to a power. So I have e to the natural log of n plus 1 raised to the power of n. Is that less than e to the natural log of n raised to the power of n plus 1? Well, what do you know about an e and a natural log? Well, and that should be in parentheses, n plus 1. They are inverse operators. So because we have e raised to the natural log of, all that stuff is going to kind of go away. And so now we're going to state that n plus 1 to the power of n is less than n to the power of n plus 1. And that makes sense to me, like conceptually, that if I take a number raised to the power of n, an exponent is really large. If I raise it to a larger power, then this thing is going to be bigger, as long as we're talking about kind of large numbers. And that's really what we're talking about on this one. We want to know that this thing will eventually kind of bounce back and forth. That's really what that's saying. It's going to bounce back and forth, and it's going to converge. That's what we have right there. So this last one, I think the notes are incorrect on this one because this thing will diverge. So this one is alternating. We have a 1/2, 1/4, 1/3, 1/8, 1/4, 1/16. It was positive, negative, positive, negative. So it is alternating, obviously. And the limit as you go towards infinity is equal to 0 because we have 0 minus 0. We have something on the bottom. So the limit of our a sub n term is going to be 0. But this thing does not decrease in value. What we're saying is that, well, actually, this is my a sub n term, and the a sub n plus 1 term is going to be the next one. So we have, and I just said the next one, that didn't make sense, 1 over n plus 1 minus 1 over 2 to the n plus 1 is that, nope. So this thing is not decreasing in value because this thing right here, the next term that we have, we'll actually do it like this, 1 over 2 to the power of n. So this is, if we end on 2 to the n, what we have to know is that this, 2 to the power of n, excuse me, that's our n term. Our n plus 1 term is going to be 1 over n plus 1. And we're saying that, actually I do need that 1, is less than 2 to the power of n. And that is not true, right? So if I move this, our next term, if I end at 2 to the n, the next term is going to be 1 over n plus 1. So we're saying that that's true, and that is not true. We can cross multiply, and we're saying that 2 to the power of n is less than n plus 1. No, anytime you have raised a number to a power, this is going to win all the time. It just choose any number, 10. 2 to the 10th power is less than 11. No, it is greater than 11. And it's going to be true kind of always. So if I ended, I don't know where I'm ended, but if I ended on 1 over n, then this would be my a sub n plus 1. So this would be a sub n, this is a sub n plus 1, right? Or in the example that I showed you, this is really a sub n plus 1, and this is a sub n. So if I end at a sub n, the next term is going to be 1 over n plus 1. So this thing, you cannot use the alternating series test to show this thing diverges. Okay? And this thing is going to, it is going to diverge, and it's going to diverge for a bunch of reasons. So let's look, if I think you would all agree with this. 1/3 minus 1, what was it? 1/8. What was the next thing? Plus 1/4 minus, you got to go back and remember this. 1/3, 1/4. The negatives are 1/8, 1/16. So if I actually look at these, and this, I'm actually going to, let's look at that. So we have this. So this is the exact same thing as the sum of 1/2, or actually 1/2 plus 1/3 plus 1/4. And the next term is obviously going to be 1/5. And then if I did the other ones, the negative values, and then plus negative 1/4, negative 1/8, negative 1/16 times 4 times 4, negative 1/64. But we know that this thing right here diverges by, all I did is regroup them. So what we're saying is that that thing that they gave you, what they gave you, the series that was given, whoops, is equal to 1 over n, that's the blue thing, plus 1 over 4 to the n. Or we would just say minus 1 over 4 to the power of n. So even though that's a geometric series that does converge, this thing diverges. So infinity minus, like this 1/4 is some sum that we could find out what it is by factoring out the negative. So we have infinity and then minus some number right here. You can figure that out pretty quickly. Whatever 1/4 divided by 3/4 is. Okay? So that does diverge, but you cannot use alternating series test. So just because it's alternating doesn't mean that it's it's going to converge by the alternating series test. A lot of times it does, and sometimes it doesn't. So the last one, and I'm not going to go over the error. That's not a part of it. What I did is you can find all of these under assignments. This is what I was talking about. The stuff I got these from AP Central. From assignments, you go to optional assignments, or you can go straight to AP Central. But I have a link of how to get there. And this is the 10.7 notes. So you can listen to another AP teacher. You either know that it converges by the alternating series test, or you cannot use the alternating series test. And we'll talk about whether or not those that you cannot use the alternating series test, most of the time it's going to diverge, but not all the time. So the first thing we need to know, if it does converge by the alternating series test, then these three things are true. It's alternating. And we need to check that it's alternating. We need to check that it's decreasing, which is saying a sub n plus 1 is less than a sub n. And then we need to know that the limit as n goes towards infinity of a sub n equals 0. Most of the time, we're going to choose those number 1 and number 3, and it's going to work. But we also need to check that it's decreasing, as we saw in that other example that I gave you. So A, is it alternating? Yes, it is. This a sub n plus 1, I actually changed that to blue. Why not? So alternating series. So we're going to test each of these individually. This is the alternating part. A sub n plus 1, negative 1 to the power of n plus 1. That means we have to the power of 1, then 2, then 3, then 4. Yes. Number C is not alternating because it's negative 1 to the power of 0, which is positive, negative 1 to the power of 2, then to the power of 4. So this would be in our alternating series test does not apply. So this will be a no. This one right here, the cosine of pi n. So if I throw in a 1, we're going to, this is me my scratch work for this one. The cosine of pi is negative 1. Throw in a 2. Cosine of 2 pi is positive 1. 3 pi is negative, blah, blah, blah. All right, so that one does, so it meets the first one. E, negative 1 to the power of n plus 1. That's a yes, because we have squared cubed. We have 0, then 1, blah, blah, blah. All right, so that's the only one that is not alternating, so we cannot use the alternating series test. Now let's go to the limit as in, does the limit reach 0? And so now we're going to get rid of that alternating. I'm actually going to change this to green. Now we're going to analyze 1 over n squared. Is that limit 0? Yes, it is. For part B, we have 2n minus 1 over 7n plus 3. Is that limit 0? No. So we have to say we cannot use it for B and C so far. For D, we have 1 over n. That limit is 0. For E, we're really looking at 2n over n squared plus 2. Yes, that limit is 0. The last one that we have is n to the 1/3 over n. That limit is 0. Okay? So the last thing that we have to figure out is it decreasing? And then we're going to put in yeses for all of those. So we have 2 no's. Is it decreasing? Is 1 over n plus 1 squared greater than 1 over n squared? The answer is yes. And also, this is a common one. So whenever you have something that actually looks familiar to you, it's like a p-series, it's going to work. It is what you have left, a p-series. We already know that's a no. This is harmonic. So this is our alternating harmonic series. Yes, 1 over n plus 1 is less than 1 over n. And we just have to state that, honestly. And this one is a little bit harder to do, but this looks like, well, this is the good news about doing the limit comparison test. They're all going to be decreasing in value and things like that. So it's going to behave, it's still going to behave like 2 over n. So this is kind of very similar to part D. This one will decrease in value. If you throw in a couple of values, you would see, and then because it is like polynomial, you're going to like it, I guess I should say. So that's going to be a yes. We can use alternating series tests, and it's the same thing. Is it decreasing in value? And what I'm saying by throwing in some numbers, you throw in a 1, and then you throw in a 2, you have the cube root of 2 over 2, that's less than 1. Then you have the cube root of 3 over 3, that's going to be less than that, right? So that is yes. And you would just have to state that the cube root of n plus 1 over n plus 1 is less than the cube root of n over n. And again, they're really just knowing that you know what the things are. And that's kind of it with that one. So each statement below is false. Correct the statement. And this is in, like I said, AP Central 10.7, the supplementary materials. So if the statement, what is this saying? Well, that's saying that it's decreasing. And the limit is 0, converges. Then the alternating series converges. Well, what is missing right here? What do we have to know about that limit? Does it have to converge? No, the limit has to be 0. That's the correction we need to make, because the limit could be like 1/10. And if the limit is 1/10, then that series does not converge. So the limit is 0. Then this is the alternating part. But what is missing? Our third thing. The third thing is missing. And you might want to press pause on this, and then try these later. So the third thing has to be true. We need to know that a sub n plus 1 has to be less than a sub n. So we saw an example where just because the limit was 0 and was alternating, but that harmonic and a geometric, put those two things together, this would be a really tricky one. So we know, statement number 3, we have a divergent alternating series. The limit of just this is 0. If it diverges, then most of the time, then the limit is not going to be 0. Right? We have an alternating series. So we would just say, the easiest thing to say is that if we know that it converges, then the limit has to be 0. We also know another thing about that one, okay? So if it diverges, the limit could be 0. But I would just, but if it diverges, the limit could or could not be 0. But if it does converge, then we are stuck. We can make the conclusion that the last term has to be 0. It is alternating, right? So consider we have some random thing, right? I don't know what that is. B sub n. It could be anything. But if that diverges, then the limit doesn't have to be 0. Let's think about our harmonic series. So we know that that diverges. And this is not even an alternating series, right? So how do we change that one? If it diverges, then we actually know nothing about that limit, right? So honestly, I just wasn't sure about this one. I had to look, and we know a lot of things about divergence. We have that alternating series. We would just take out what they did on the AP Central. Was they said, just take out the if and then part. So we would just, actually, you can change that one. If the limit of b sub n doesn't equal 0, we actually change that to if the limit of b sub n, whoops, of b sub n, as n goes towards infinity, doesn't equal 0, then we know that that one diverges. That same infinite series diverges. Now let's look at an AP Central, a practice exam about things they would ask you to know about alternating series. So is this thing alternating? Yes, it is. Use the alternating series test to show that that one converges when x is 3. So when x is 3, so we have, I'm actually just going to, I don't even know, honestly about this one. X is 3, let's see what happens. So we have -1 to the power of n, 3 to the 2n over 2n factorial. Okay? Use the alternating series test. So we just need to state the 3 things that are true about this one, honestly, and not even worry about this. So, so since the series is alternating.
I didn't get that. Could you try again?
Whoops. Is it alternating? And I would do.
Get that. Could you try again?
And the limit as n goes towards infinity of 3, and I'm just going to use that the non-alternating part, 3 to the 2n over 2n factorial equals 0. And you would just say that 3 to the 2n plus 1 over 2n plus 1 factorial is less than 3 to the 2n over 2n factorial. The series converges. Right, you just state the 3 things. It's alternating, the limit is 0, and that test, and it is decreasing, right? And there's really, the limit is 0 for this one. And that's really all there is for that one. Show that this series converges for all values, for all x values where x is a real number. So what would we use on this one? So we would use probably our ratio test on this one. So we have, by the ratio test, let's see what happens. We do the limit as n goes towards infinity. And since we're doing an absolute value, it kind of, we'll actually write that in there. -1 to the power of n plus 1. And then we have x to the 2 n plus 1. Whenever I have whenever a number with the n, it becomes a little bit trickier. Over 2 to the power of n plus 1 factorial. That whole thing is going to be a factorial. Times, now we have to have 2 to the power of n over 2n factorial, excuse me, negative 1 to the power of n, x to the 2n. What is that limit? And I probably didn't give myself I didn't give myself enough room on that one. So since we're inside the absolute value, then those things go away. Okay, so that goes away. And we don't have anything else that is exactly the same. So we need to focus on rewriting this. So it's 2n plus 2. So that's going to be x to the 2n times x squared over 2n plus 2 factorial, which means it's 2n factorial times 2n plus 1 times 2n plus 2. So that one is, yeah, I'll do that on another slide, show you how I got that. 2n factorial over x to the 2n. So that now cancels out right there and right there, right there, and right there. And so we can say that this next one is going to be really easy. So I don't need any more room for that one. The limit as n goes towards infinity over x squared over 2n plus 1 over 2n plus 2 equals 0 if x is a real number. If x is a real number, then it's less than infinity. So any real number divided by infinity is always 0. And that's what you would have to, actually I won't do it at the bottom. So we have 2n, what was in my head, 2n plus 2 factorial. As you kind of know, that means x, 1 times 2, and then we'll get to n, then we get 2n, then we have 2n plus 1, then we have 2n plus 2. So if you think about like n is, let's let n be 3. So this is saying that I want, this really is 8 factorial when n is 3. So I have 1 times 2 times 3 times, so if I have 3, that's really like 8 factorial. And we're looking at what is 2n plus 2 factorial. So 8 factorial, or any number n, is 1 times 2 times 3 times 4 times 5. And then we eventually get to 6 factorial. And that's because that's 2n. And then 7 factorial, and then 8 factorial. So we need 2n. The number after 2n is 2n plus 1. Then the number after 2n plus 1 is 2n plus 2. So it doesn't go straight from 2n factorial to 2n plus 1 plus 2 factorial. You have to have these next numbers after 2n. So that's why that is 2n factorial, they cancel out, and we have 2n plus 1 and 2n plus 2. It's probably the easiest way for me to explain that. So consider the function where this is the derivative. This is blah, blah, blah. But fortunately, they wrote it out for us. Determine whether that f has a relative max or min at x equals 0. So if it has a relative max or min, we know that the derivative has to equal 0 or undefined, right? That's what we know if it has a relative max or a min. And then we would have to know whether it changes or whatever. When x is 0, so we can just throw in 0 into all of those. So the derivative at 0 is going to be 1 plus 0 squared over 2. Sorry, that should be a minus. Plus 0 to the 4th over 4 factorial. Minus, and it keeps going. So we can just say that that's 1. So since the derivative is 1, we know it's increasing. So it's still going up. So it's got to be neither. Since f prime of 0 not equal to 0. We can say that since f prime of 0 equals 1. We already showed that it wasn't equal 0 and it's not undefined when we said that it equaled 1. So that is it for alternating series and a couple of things you can find on AP Central with better handwriting. So if you have any questions, please stop by and ask those questions during office hours or send me an email.